Hello, my name is Timo Striff. I'm CTO of emmtrix Technologies. Emmtrix is a small company in Germany, and today I want to talk about our ONNX-to-C compiler. And we had the goal of the project to have 100% test coverage for the ONNX test cases. And today I want to talk about our lessons that we learned while building this compiler. My talk is structured into 3 parts. First, I will talk about the project and the approach. So what is ONNX-CGen? How do we use it at emmtrix? Then I will talk about 5 lessons that we have learned during development. And finally, I will provide a status about the project. So what is ONNX-CGen? ONNX-CGen is an ahead of time compiler that converts ONNX models into portable deterministic C code. So thereby it applies a correct net first approach. That means this generated C code must be correct and comparable to the ONNX runtime. The goal is that the C code is runnable on embedded systems, especially deeply embedded systems, so without dynamic memory consumption. So there is not allowed to use malloc, free, no heap. Everything must be static, and memory must be also managed at compile time. So there is no requirement that there's an operating system or an external runtime. And it generates readable and auditable Z code that is also especially used in certification environments. And very important is that it supports dynamic models. So on the right side, you see an example of a model. We have one input function, the model function. The input parameters of the models are function parameters. So here A, B, and C, and one output parameter. And then it calls 3 functions, 1 function per node. And one implementation of a node function is here an example. That is a component-wise multiplication that just multiplies 2 elements. And we use here an encapsulated scalar function so that it can be reused. So how do we use ONNX-CGen at emmtrix? So ONNX-CGen is for us in front end, where we first generate generic C code and then we apply our generic compiler to optimize that C code for embedded target architectures. Here, for instance, an Infineon architecture, and where we do a lot of optimization, vectorization, and so on. So in principle, Z is thereby our intermediate representation, so it's comparable to MLIR, but it is not MLIR. It also has a stage lowering process, but it relies on a standard. So C, that means every intermediate step is testable, reviewable, and it's toolchain agnostic. That means we can use any C compiler at the end, especially also qualified ones. And our approach is that we first generate correct C code, and then we make it fast in a later step. And it is operator agnostic, so that means for our optimization here, we do not need to know the operator in advance. And our heart, we have a source-to-source compiler which modifies the C code, and we apply here transformations like node fusion, memory reduction, vectorization. We optimize the memory layout, we reuse buffers, and we also make offloading of weights and copy them into faster memory. Here's just one example of a RISC-V code with a vector set extension. So if we want to support 100% test cases, we also need to support all data types. So I have here a table with ONNX data types and the Z representation. So integer and bool are straightforward. Float and double is also straightforward for 16-bit floating point and 16-bit B floating points. There's is it different? So 16-bit float is supported in Z23, but B float we need to use Clang or GC extension. For sub-byte integers, we have now also support in Z23, but there's only a drawback that if you store an array of bit ints on the memory, they will always consume 1 byte, so there is a space wasted. For low precision floating point like 8 and 4-bit, there is absolutely no representation currently in C. So we currently do emulation. So it's more marketing to get 100% coverage, but it is not efficient or performant. If that is required in future, we will take a look how to efficiently apply it. Then there are strings, sequences optional that are directly mapped to arrays and sometimes with an additional variable for the count or is present. Then there are data types that we do not support because we haven't found test cases for it, at least in, maybe I missed something. If test cases appear, we are happy to also support these. This directly leads us to our first lesson. So in principle, ONNX is effectively unbound. That means it is for specific type of ONNX models impossible to make a static memory allocation without restrictions. That starts already with strings. So strings are unbound. They can grow in the length infinitely. So one string can consume the whole memory of the PC. So what we do is we just apply one global setting and restrict the string to 256 bytes. So it's changeable, no problem, but we waste here a lot of space. Same thing for sequences. Sequences, the containers, they have no capacity, so we just restrict the sequences to a fixed maximum length or capacity, by default to 32. And the other are dynamic dimensions of the input parameters. Here, it's at the beginning unproblematic because dynamic parameters are not allocated by the model. It's allocated by the function that calls the model. Then it also uses internal, which is stack variables. That's also no problematic. Problematic is only if the stack is too small. We don't know how much stack will be consumed by dynamic dimensions. So sometimes we support changing or allocating temporary variables on global memory. And here the problem is that we don't know the upper limit, so this is currently unsolved. So the next problem is that for sequences, the element type is underspecified. What does this mean? So if we have a sequence, we only know, okay, there is a tensor or float maybe inside, but for the tensor, it is unknown how many dimensions it has, what is the rank, and also what is the size of a specific dimension. And there are even sequence types called rect sequences that can completely vary for every item. And for a compiler, we must resolve that ahead of time. That's nearly impossible. So the only solution that we found was that we need additional information. So we added a command line parameter so that we can specify for sequence input parameters the maximum size and the shape. And for instance, here we have boxes input, and we define here, okay, it's two-dimensional. The first dimension is up to 100 elements. Second is fixed to 4 elements. That is what we do in the compiler, but it would be better if that is would be part of the ONNX type system, so that we can directly define in the ONNX model this constraints of we have here a sequence of a float tensor, and it has here maximum length, and it has 2 dimensions and the restrictions for that. And that could be directly represented in ONNX graph with a type proto or tensor shape proto fields. So the next problem is type and shape inference. That the type and shape inference that is available for ONNX is not sufficient. So it simply starts that inference is not specified for all operators. Very often shape depend on values, attribute, or subgraph. So you have to do a lot of hacks and special implementation to make good inference out of it. So right now, our compiler and also other compilers like MLIR are responsible for that. So in general, there's a problem that there is no reliable standalone library for shape inference for dynamic lattice to support symbolic inference is available. And our vision is that in future we will close the gap and have a shared and extensible interference layer. And shared means that we define a language, a domain-specific language, that can describe for each operator how type and shape inference is performed. And this can be used by C++, Python, or any other language to derive shapes, either in a numerical or in a symbolic way, depending on what you need. And the really cool thing is that this DLL could be also directly stored in ONNX model. So if there's an unspecified operator or an unofficial operator, maybe from ORT, it can store how shape should be inferred directly in the DSL. And what also could be done is that we do not just store how shapes are inferred, but the result of the shape inference directly in an ONNX model in a way that dynamic marbles are supported. So one problem during implementing of the project was that, at least in the middle, that we did not know how important is one operator. So there is only this offset versions, and there's a huge catalog of 200 operators now in ONNX, but it's completely unclear which are the common ones, what are the critical ones, what are niche operators. So the priority of supporting operators was for us more guesswork. For instance, there's this image decode, which is pure pre-processing. So if you want to support pre-processing, that's fine. If not, you don't need to implement that. And that was also hard to plan what operator to implement next. And to address it, we have 2 ideas. One is that ONNX could define an operator category. So it's a core mass, neural network layers, pre-processing, and so on. And then backend authors can prioritize on the specific category what they want to support. And second idea is more some experimental basis, so that we could make an operator atlas. So on Hugging Face, I think there are around 40,000 ONNX models available, so we can analyze it and then provide what are the what operators are used in the wild and all with which data type. So then you can just support the ones that are mostly used. The last lesson is that the evaluation order and precision are unspecified for all operators. So ONNX only defines the mass, but not how something is evaluated. If we, for instance, take a look at a relatively simple operator, the reduce sum, that sums up one dimension, there are at minimum 3 ways to implement it for 32-bit floating point. You can use a linear implementation. You just sum up everything in a variable. So that is a typical implementation that we have. If you want to have a lower error, you can make a pairwise sum up, which is more complex to implement and requires also intermediate memory. Or you can use an 64-bit floating point for accumulation, a wider data type. That gives you the best result. But the consequence is, so it is not defined what is correct. Only the ONNX test cases are typically using NumPy, and they are using this 64-bit accumulation. And for that reason, we by default use this one because it's faster. And for test cases where we could not fulfill the accuracy requirements, we tuned our test cases that for these test cases we just use the 64-bit accumulation method, so we can specify by command line parameter which methods to use. So now to the status of the project. So from ONNX, we support the latest offset that was released, I think, last week. We also support a relatively new ORT runtime. At least all operators. We have the side project. We could derive ONNX-like test cases with an ONNX file and PP files out of the unit tests that are embedded in the ORT. And then we also have a backend implemented and are part of the backend scoreboard. And there we are on the second position from supported test cases point of view. And there we are right behind the ONNX reference. And so you can see here the number. So we achieve 98%. So the gap of 2% is the missing data that we need for specific test cases that we support, as like shapes and constraints and so on. In our internal test suite, we achieve 100% test coverage for ONNX and a very good test coverage for the ORT. Finally, I want to thank you for your attention, and I'm here for answering questions. And I want to thank Andreas for bringing me into the ONNX community.